A study performed on transformer failures found the following information. 51% were classified as winding failures, which include turn-to-turn failures, surges due to lightning, moisture, external faults, overheating, open winding, or deterioration. 19% were related to a mechanical failure of the tap changer. 9% were attributed to bushing failures due to aging, contamination, or cracking. 6% can be traced to loose connections on the terminal board. 2% were due to core insulation failures. And the remaining 13% were simply classified as miscellaneous failures. The percent differential protection element, which is considered the primary protective element for transformer protection, can detect most of these failures. Differential protection. As stated, the primary protective element for the transformers is the percent differential element, which compares the current entering and leaving the transformer. Modern microprocessor-based transformer percent differential relays, such as the GE Multilin T35, T60, and SR745 relays, have built-in compensation for the turns ratio and phase shift, and so neither of these topics will be addressed. For further information on the percent differential element's theory of operation, please reference the percent differential section of this course. When applying differential protection to a transformer, there are several factors that must be taken into consideration, which are magnetizing inrush or second harmonic, fifth harmonic current, voltage per hertz, arc detection, and sudden pressure. We will now examine each of these issues. Magnetizing inrush or second harmonic. This is a normal characteristic of a transformer that is being energized. When the system voltage is applied to a transformer at a time when the steady-state flux should be at a different level from that existing in the transformer, a current transient, known as inrush, occurs to build up the flux. Inrush currents between 8 to 30 times the full load current flows into the transformer with no current flow out. This current flow would normally appear as an internal transformer fault to the differential element. However, many years ago it was determined that there is a large second harmonic component of this inrush current. Modern microprocessor relays include a harmonic restraint feature to assure that the relay will never operate on inrush. Let's take a closer look at harmonic current restraint. The principle of harmonic current restraint makes a differential relay self-desensitizing during the magnetizing current inrush period, but the relay is not desensitized if a short circuit should occur in the transformer during the magnetizing inrush period. The relay is able to distinguish between magnetizing inrush current and short circuit current by the difference in wave shape. Magnetizing inrush current is characterized by large harmonic components that are not noticeably present in short circuit current. A harmonic analysis of a typical magnetizing inrush current wave was as shown in the accompanying table. Fifth harmonic current. Transformers that are connected directly to a generator that is brought into or removed from service, or the failure of an upstream tap changer, may result in an overvoltage condition. If the applied voltage rises above the rating of the transformer, known as overexcitation, a fifth harmonic current is generated. Depending on the amount of overexcitation, this fifth harmonic current could rise to a level that could cause the main differential element to operate. Short-term overexcitation is a common occurrence on a power system and is especially true for transformers connected directly to generators, and so this element is used to restrain or block the main differential element from operating when fifth harmonic currents that are present are large enough to cause the main differential element to operate. Voltage per hertz protection. Transformers must not be subjected to prolonged overvoltages. For maximum efficiency, they are operated near the knee of the iron saturation curve, such that slight overvoltage results in significant exciting currents in the transformer. The voltage per hertz element is set up as a backup to the generator control system and the differential element when blocked by the fifth harmonic restraint feature just discussed. It is recommended that two voltage per hertz elements be set up, one at approximately 110% to generate an alarm and trip in about a minute, while the second is set to approximately 120% with a trip time around 6 seconds. Arc detection. When a high or low-level fault occurs within the transformer, usually an arc forms. This arc causes the oil within the transformer to break down and gas is formed. The speed at which the gas is formed is proportional to the size of the arc and hence the fault. The transformer design determines how this gas is detected. In European transformer design, there is no space for the gas to collect, so a conservator tank is connected to the transformer. A gas accumulator device, known as a Buchholz relay, is connected between the transformer and the conservator tank or tanks. If a low-level fault results in arcing, the small amount of gas that is produced will accumulate in this relay, which will then issue an alarm. If there is a sudden large increase in the amount of gas being produced corresponding to a large fault, the relay will sense this and trip the transformer offline. Sudden pressure. In North America, oil-immersed transformers will have sudden pressure sensors. One style will operate on a sudden change in the oil, while the other operates on a sudden change in the gas above the oil. They have inverse time characteristics, meaning they will operate very quickly for a high-energy arc and trip the transformer offline, while they will operate slower for a lower energy arc and may at first only issue an alarm.